Hello everyone. Today we will discuss an important topic, the multivariate optimization. Now, when we say optimization, it is nothing but the quest for the best. It is of immense importance in consumption and production theory, in economics, so that the best alternatives can be chosen at a desired level. Now, process of optimization deals mainly with maximization of utility of a consumer, or maximization of profit and minimization of cost of a producer, or to increase the yield to maximum level. So it will find the set of values of the choice variable that will yield the desired extremum of the objective function. So optimum level can be examined with or without constraints. So we know that in production as well as in consumption there are constraints. In consumption there will be constraints of income. So also in production there will be constraints of cost. So under such constraints, how to find out the optimum levels? Now here we will deal with the multiple choice variables in examining the desired extremum. So instead of considering a single choice variable, we will consider here multiple choice variables. Suppose y is the function of x1, x2, so on up to xn. So earlier in several examples we have considered y is the function of x only. X is a choice variable or independent variable, but here we will consider more than two variables, what we term it as multivariate optimization. Now there are two processes of optimization, one is constrained and one is unconstrained optimization. Now let us discuss unconstrained optimization. There are three choice variables. Z is the function of x1, x2 and x3. So for simplicity or handling by hand, let us take three choice variables. Z is the function of x1, x2 and x3. Now when the function is specified, now here function is not specified, function will be specified with data. We can find the conditions for maximum and minimum. Suppose is a consumer's behavior. So how a consumer will maximize his utility, he will buy goods. So how utility will be maximized by those goods. Okay. So similarly, minimum. Now a farmer may use several inputs. So what will be the minimum cost for that? So for maximum, our first order condition should be put to 0. So F1 means delta y by delta x1 or delta z by delta x1, that is F1, put to 0. So delta z by delta x2 put to 0 and delta z by delta x3 put to 0. So this is the F1 is equal to F2 is equal to F3 is equal to put to 0. This is the first order condition. Now second order condition, f11, that means what f1 we will get, we derive again with respect to x1, that is f11. So it should be negative for maximization. And this should tell you f11, f22 should be greater than f12 whole square. So f11, f22 means first derivative with respect to x2. What result you will get, again you will derive with respect to x2, that is f22. So multiplication of the product of that should be greater than f12, that means partial derivative with respect to x1, what result will come, again derive with respect to x2, and that is f12 square. So this should be maintained. Now in case of minimization, first order condition is same, and second order condition f11 should be positive. Here it is negative. In case of maximization it is negative, and here it should be positive. And f11, f22 should be greater than f12 square. Now this determinant f11, f12, f13, because we have three variables, f21, f22, f23, f31, f32, f33. So if it is negative, it is the maximization problem. The function will be maximized. It is a maximum problem, maximization problem. And if it is positive, it is minimization. If we are to generalize, suppose instead of x3 variables, x1, x2, x3, we have considered many variables. So x1, x2, so on up to xn, because it is not always true that a consumer or a producer will be limited with 2 or 3 choice variables. A consumer may buy many commodities. Some of it may be substitutes, some of it may be complementary to each other. And so there will be many commodities. So the general notation, suppose utility or u is the function of x1, x2 and xn variables. So for maximum, now the differential conditions, du should be equal to 0 and d square u, second differential, second order, should be negative. This is for maximum. And for minimum, du is 0 and d square u is positive. So earlier we got f1, f2, f11 and so on. But here in general notation, the first order condition is du should be equal to 0 and second is d square u is negative. And for minimum, du is equal to 0 and d square u should be positive. And what is du? Means differential of the function f1 dx1 plus f2 dx2 plus so on plus fn dxn is equal to 0. As xi variables are independent, so f1 is equal to f2, so on up to fn is equal to 0. Then second order condition, d square u, as we said, is second order condition, f1 dx1 plus f2 dx2, so on, plus fn dxn squared. So this is du, square is d square u. And this can be written as dx1, dx2, so on to dxn and this is the Hessian determinant multiplied by dx1 again. This is nothing but this. It is a quadratic form and the associated matrix is real and symmetric. D square u to be negative, the quadratic form should be negative definite, and the principal minors of the matrix will alternate in sign. Then f11 less than 0, that means negative. f11, f12, f21, f22 should be positive, and so on. Next will be negative, next will be positive, and like this. So it holds d square u should be negative. Now in case of minimization, this is for d square u negative, this is for maximization. Now in case of minimization, du is 0 and d square u is positive, greater than 0. The secondary condition, d square u positive, greater than 0, that means positive, will be satisfied if the principal minors of the associated matrix of d square u are all positive. It means f11 greater than 0, positive, then f11, f12, f21, f22 determinant is positive, so it is positive. So in case of minimization, so the associated matrix of d square u should be all positive. Let us do one exercise. So u is equal to 4x plus 2y minus x square minus y square. Now what is fx? So variables are x and y. It's a multiple variable, x and y. We can write fx or f1. If x is 1 first, y second, then it is f1. So 4 minus 2x is equal to 0. Fy, 2 minus 2y is equal to 0. So first derivative with respect to y, first derivative with respect to x. So from here you can find out x is equal to 2, y is equal to 1. Now what is second derivative? Fxx. It is minus 2. Fyy, again minus 2. Fxy, fx with respect to y, and there is no y, because we will have to derive from this. So there is no y. It is 0. Similarly, fyx, there is no x, it is 0. So that's why fxy is equal to fyx is equal to 0. Now if we see fx is negative, less than 0. Now fxx, fxy, fyx, fyy, the determinant of this is equal to minus 2, 0, 0, minus 2. If we put this values is equal to 4, which is positive. It indicates that d square u is second order condition is negative. It is the case of maximization. Okay. Then another example, x1 square plus x2 square plus x3 square minus x1 x2 minus x2 x3. So here also, if we find out the derivative fx1, fx2, fx3, fx1, x1, that is f11, f22, f33, then f12, that means x1, x2, then fx1, x3, 21, that means f, that is partial derivative with respect to x2 and x1. Like that we can get it. Now multiplication of that. fx1 x1 into f x2 x2 is equal to 4, and square of this is equal to 1. So 4 is greater than 1. It is satisfied. Then determinant of this is equal to, if we put these values fxx, x1 x1, x1 x2 and so on, 2 minus 1 0, minus 1 2, minus 1 0, minus 1 2. So determinant of this will be equal to 4. So it is a minimization function as the secondary condition is satisfied. It is a minimization function. So examine extreme values. So just for exercise, z is equal to 3x1 square minus 4x1 x2 plus 7x1 square.